Hey everyone, and welcome. So today we're going to dig into this really cool conversation that, it starts with what seems like a simple question about batteries, but it ends up unpacking something way bigger. A really powerful way to think through almost any problem. It's a fantastic case study in first principles versus just doing things the way they've always been done.
So this is the puzzle right at the heart of it. You've got these huge, modern, super powerful lithium batteries. The power stations you take camping or use when the power goes out. These things can run a fridge for hours on end. So why in the world can't one of them deliver that quick, powerful jolt needed to jumpstart a car? I mean, it really seems like it should be able to, right?
Okay, let's get right into it. To really get our heads around this, we first have to understand the conventional thinking. Why everyone sees these two gadgets as totally separate things in the first place.
And this just lays out the standard argument perfectly. On one side, you have the power station. That's your marathon runner. It's built for a nice, steady, low and slow output, maybe 10 amps for a really long time. Then you've got the jump starter. That's the sprinter. Its only job, its entire reason for being, is to unleash this massive blast of power. We're talking hundreds of amps for just a couple seconds. Two completely different athletes for two completely different events.
And this is where that simple, brilliant question comes in. Someone looks at one of these new, high-tech lithium iron phosphate batteries and just goes, hold on a minute. This isn't some old lead-acid battery. This thing is an absolute beast. Why can't our marathon runner also do a quick little sprint? And that, right there, is a fantastic question.
So, let's move on to what usually happens when you ask this question. You go to an expert and you get the standard answer. It's fast, it's firm, and honestly, it sounds really, really convincing. The very first thing you'll hear is just a flat no. Not, maybe, or, well, it's complicated. Just an emphatic, nope, you can't use a leisure battery to jump a car. Don't even think about trying it. So what's the actual reasoning they give for that hard no?
And this right here is the technical wall you slam into, the Battery Management System, or the BMS. The best way to think of it is as the battery's own personal electronic bodyguard. Its only job is to protect those delicate lithium cells from anything dangerous, and a huge, sudden current draw is at the top of its list. A car's starter motor is incredibly greedy. It asks for way more juice than the BMS is programmed to ever allow. So the second it tries, that BMS bodyguard just steps in and cuts the power. End of story. Case closed, right?
Well, not for the person who asked this question. Nope. They didn't just accept that this little electronic gatekeeper was the end of the road. They started pushing back. Not with opinions, but with hard data and a much deeper look at the actual physics involved.
So they come back with the actual spec sheet for a specific leisure battery. And look at that. It says right there it can deliver 200 amps continuously and a peak of 300 amps for 3 seconds. Well, that sounds an awful lot like what a small diesel engine might need to get going. The numbers seem to match up. All of a sudden, the bodyguard's rules are looking a little negotiable.
Now this slide brings us to the next big roadblock, Ohm's law. So the expert's argument has to shift. They say, okay, maybe you can get around the BMS, but you can't get around the laws of physics. A starter motor has super low resistance. You apply voltage, and it just tries to suck down a massive current. The only way to limit that current is to add more resistance. But as you can see from that simple little formula, there's always a catch.
And that catch is an absolute killer. If you add a resistor to choke that current down to a safe 200 amps, it also causes a huge voltage drop. The starter motor would end up getting just a trickle of the power it actually needs. It might groan a little, but it would never, ever spin fast enough to start the engine. Yeah, it's exactly like trying to put out a fire with a fire hose that's being fed through a tiny little straw.
But again, our questioner refines their thinking. They ask, well, what about a smarter solution? Not just some dumb passive resistor, but an electronic one, like a MOSFET that could actively control the current, keeping it right at 200 amps. I mean, that's totally possible with today's tech. And this is where the whole argument takes a really, really interesting turn. The expert's counterpunch is simple. Heat. A ton of heat. See, a MOSFET acting like a variable resistor would have to absorb all that extra energy, and it would get ridiculously hot. The key number is right there on the screen. 2,000 watts. That's literally the same amount of power as a plug-in space heater, all being dumped as pure heat into one tiny little electronic component. It sounds like an absolute showstopper, a total thermal nightmare.
Okay, let's move on to the real turning point in this whole debate. Because this is the part where a simple, real-world observation completely takes apart that supposedly insurmountable heat problem.
And there it is. It's so simple, it's brilliant. The questioner just points out that we deal with this much heat all the time. A toaster, a kettle, your oven, these are all devices that handle 1,000 to 2,000 watts of heat. We know exactly how to manage it. It is a completely solved engineering problem, not some unbreakable law of physics. The so-called thermal nightmare is just a matter of design.
And then they deliver the final devastating blow to the whole argument. They ask about the heat that's generated inside the battery cells themselves, because every single battery has some internal resistance. And when you pull huge currents from it, that resistance creates its own heat. So just how much heat are those cells already dealing with on their own?
And here's the number that just changes the entire game. During that 3-second high current burst, the battery's own cells are generating nearly 500 watts of heat internally. Just think about that for a second. They're already getting incredibly hot with no fans, no heat sinks, inside a completely sealed box. And they're designed to handle it just fine.
And that is the mic drop moment. The original argument that adding an external circuit would create this unmanageable 2,000-watt heat problem, it just completely falls apart. The cells themselves are already taking a massive thermal hit and shrugging it off. The thermal problem was a red herring. It was never the real barrier.
So with all the technical objections basically cleared off the table, we can finally see what's actually going on here. And, surprise, surprise, it has a lot less to do with physics and engineering and a whole lot more to do with history and marketing.
Let's just quickly recap what we've figured out. First, the physics says the cells can totally handle the current. Second, the engineering required to build a boost mode is dead simple. A few cheap parts like resistors and relays, that's it. Third, the thermal load is completely manageable. And finally, the cost to add this feature, it would be tiny. There is no real technical barrier here.
The real reason this doesn't exist is just market segmentation. It's a holdover. See, back in the old lead-acid days, starter batteries and deep-cycle leisure batteries were chemically and physically different. You had to have two separate products. But modern lithium technology basically erases that distinction. The thing is, the companies making them just inherited this split market. They keep selling leisure batteries to one crowd and jump starters to another. And no one's really stopped to question if one product could now do both jobs.
And this whole journey brilliantly illustrates a framework for thinking through almost any problem. Step 1, ask what the fundamental laws of physics say is even possible. Step 2, ask what current engineering says is practical to actually build. And only then, as step 3, do you look at what the market is selling and ask why. And so often the reasons you find in that third step are just inertia, habit, and history, not fundamental limits.
And that really brings us to our final thought. This was never just about batteries, was it? It's about a way of thinking. So, I'll leave you with this question. What other things out there in your world, things you've always been told are impossible, are really just market habits disguised as engineering problems, or engineering problems disguised as unbreakable laws of physics? Something to think about. Thanks for tuning in.